Welcome to today's lecture for an introduction on classification. So the main goal of this lecture is to understand the sensor data and to interpret what different parts of this sensor data actually are. For example, if we have an image of an outdoor scene, say on a highway taken from an autonomous robot, for example, or a car, and we want to figure out, let's say, which parts of this image are roads, which part are buildings, where are the humans, etc. So we want to kind of extract certain semantic meaning from our sensor data. So this would be the primary goal for this lecture, and we'll kind of look into techniques which helps us derive such information from the sensor data. We'll primarily focus on one such family of algorithms, which is also called as supervised learning methods, where we essentially show certain examples to these systems from the past. We label them, we say, okay, these are some of the labels for the objects that are there in the surroundings. Can you use these examples and say something about future data, so data which hasn't been seen yet? In the course of the lecture, we'll also introduce a few different metrics which would help us characterize how good a particular classification system works. So this also kind of gives us tools to choose between different classifiers for our application. And finally, we'll introduce two fairly simple classification systems which can be used for interpreting the data like I just mentioned. So to get started, let's see an example from the agricultural robotics field where, for example, you get this kind of RGB image from a UAV which is just flying over a field, and the classification problem here is to detect the vegetation. So which means, given this image, I want to understand which parts are the plants or other kind of plants that are there in the field, or other crops that are there in the field, and come out with an image like this which says for each one of the, or for each white pixel, this is the crops, whereas the black is the background, which essentially is the soil. So the classification problem here is, for each pixel in the image here, tell me if that particular pixel is a vegetation point or not. Right, so this kind of example is useful in terms of analyzing the crop growth, etc. But what we are doing is to convert our raw data, in this case an RGB image, into a data which we can interpret as vegetation or not. So this is just one example of what a classification system would look like, or what a classification problem is. So if we want to formalize this a little bit more, we can say for a classification problem in general, the idea is that we get some raw data, and then we want to figure out what are the various classes, or what are the various labels, objects that are there in this image, for example. And in this case, we have k different, in general, we could have k such labels, so k such objects. So in the example that we just saw in the previous slide here, we have two classes. One is the foreground, which is the plants shown here in the white, and the background, which is just the soil. But in principle, we could have many more classes. So for example, within the crops itself, we could say this is plant of type 1, plant of type 2, weeds, or whatever, and so on. And therefore, in a general classification problem, we could have k different classes that we want to identify here in our sensor data. And what we give as input to the classification system is what is called as this feature vector E, which is a representation of our input data. Again, going back to our example here, our input E could be the whole image. So this could be the intensity values for each pixel of our RGB image, but this could also be something more. For example, we could compute, just as an example, the contours of the plants, so the outer structure of the plants, and we could put this information into our E feature vector. So essentially, this E is something that kind of explains our input data and helps our classification system to say what this particular region could be. And the goal of a classification, or the goal in a classification problem, is to come out with this function f, which, given this feature E, spits out a class for that particular feature vector. So for example, here E could be the entire image, F could be this mapping which takes in this E vector and tells me what class is that particular feature vector represent. So this could be done at different levels. So in the sense that you could take the whole image as one feature vector and then say an output. So for example, if you take this whole image as, let's say, you want to get one label for the whole image, it could be something like a field, right? So this represents a field, and therefore given this image you want the classification system to say, yeah, this is a field. In that case, this C would be a field. But you could also do something at a much more finer resolution, in the sense that I want to understand what each one of the pixels is. Then the E would correspond, the feature vector E would correspond to what the information for that particular pixel is, and then it could give a per pixel information as to, okay, this pixel here is a plant pixel or a crop pixel, this one here is a background, and so on. So this is the general framework of how a classification system could look like. So again, just taking the previous example, so these features, what I said E, could be, for example, the intensity values at the different points. So if I take this point, I look up the R, G, and B, so the red, green, and the blue values of the image there. And this could be one of the features that the classification system, the classifier, takes as input. And the output would be, okay, that particular pixel is a vegetation pixel, or no, it's just soil, or it's a background. So this could be one example of a classification problem. So of course, fields are not the only place where classification is useful. So there are many other applications. For example, we want to detect humans in a particular image. So in this case, I guess this is from a music video, but we want to figure out which are the which parts are occupied by humans, and this is described here by these green pixels overlaid on the humans, right? So if we know this kind of segmentation of the image, we know, okay, this parts are by human, and then we could use this information for further things in our application. And the example on the bottom is the one that I started our introduction with, where, for example, we have an image taken from a car, and we would like to understand what the different things are around us in the environment. So in this case, for example, this lighter pink area here corresponds to the road areas, whereas this other shade, the darker pink, are the, let's say, the footpath areas. Then we have lampposts, people, etc., which are also being detected here. So the idea is to take in the raw image or the raw data, in this example an image, and spit out different semantics, or to understand what are the different components of this image. And these are some of the examples of a classification, or what a classification system can do. So let's look at one more example, which is a rather traditional or classical example, also called as the OCR, or optical character recognition example. So if you have written letters to your friends, you know that parts of this are actually automated, in the sense that, for example, if you write the PIN code at the bottom of your letter, these are often not read by humans, but rather by machines, which try to figure out what those numbers are, or what those letters are, by just scanning the portion of the of that region of your letter, and figuring out what those characters there are. So this is just one particular way in which a classification system can be designed, and let's see how or what are the components which form such a classification system. So of course you write something on your piece of on your letter, and then let's say it's been binarized, so it's been scanned, and you get a representation like here. So essentially here all the white pixels, say, are zeros in this case, and the black ones are 1. What you can do is you have this a square, or you have, for example, let's say 20 cross 20 pixels here, and then you can convert this input image into a feature vector E as a string, as shown here. So this image may be represented as, let's say, 0 0 0 0, so some zeros, and then ones where there is this black part, and so on, and we end up with this representation for that image, which is a string, right? So this is a choice. So this is a design choice about how you want to represent your input image. In this case, we say that we represent it as a binary strings, with zeros where there is no mark or there's nothing written, and 1 in the places where there is actually something written. And then this kind of goes into our classification system, and which spits out the class of that particular image here, which says, okay, it's the character A that's been written here. So in this example, the classifier here operates by the principle that it would return that class which is most likely given the feature vector E coming from here. So this classification system here says that, okay, what's the probability of my image being, for example, A, so omega is equals to A, given E, which is this feature vector, right? And if you know a little bit from Bayes' theorem, you know that this usually constitutes of two parts. One is what is called as the prior information of your image or of your data, and one is the likelihood. And so, for example, if you think of the prior information, so we know, for example, if we are writing in English, right? So we have these characters A to Z, and usually we know that, let's say, some of the letters are more occurring than the others. For example, A or C or S are often more occurring in English than other letters, right? And therefore, for example, we could use that knowledge to say that, okay, given our input image, for example, there is there's a higher probability that that character is, let's say, A over, for example, Q, or Z, which occurs much fewer. Right? So this is kind of the prior probability that's involved in there. The other probability that's involved in there is like, okay, so given a string, what's the likelihood that it's some particular character? So given a string, like shown here, what's the probability that it's A? Of course, this is a little bit more tricky to model. For example, I may write the letter A in a slightly different way than you would write it. And therefore, this means that there are multiple E's for which we actually mean A, right? So I may write it slightly slanted, I may write a small a, I may write a bigger A, and so on. And this means that having this information is often quite difficult. But let's say we get this information some way, we can then fuse the prior information coming from here as well as the likelihood information coming here to figure out what is the most likely class given this string that we have here, and this would form our classification system for this example. Right, so this is one way in which we can build a classification system to understand, okay, what is the character that is written here. Right, so like we saw, so these probabilities here, especially the likelihood probabilities, are often very difficult to manually specify. And the idea here is that we need certain additional information to actually learn this function f, right? So the function f, which maps our features to our class. So in the previous case, although we don't explicitly see the function f, essentially function f deals with this portion here, which tells us once given a feature vector E, what is the class corresponding to that vector, right? And this additional information often can be provided through what is called as the training data. Or, for example, if I give, let's say, 100 examples of how A looks like, I could convert them into these strings of E's, so the binary strings, and then learn from there what A looks like from the writings of different people, right? So often these probability distributions, since they're really difficult to specify as rules or as to kind of give it in a generative manner, we actually learn this from the data itself, right? And this leads us to the idea of the training data, right? So we want to learn about the probability distributions through data rather than directly specifying how a particular character, for example, looks like. And this is done in the following manner. So we collect, let's say, n examples. We ask n different people, let's say 100 people, to write down the character A, to write down the character B, and so on, write down all the numbers and so on. And we collect those data points, and this forms our examples of training data. So what would happen is that we would have these E vectors, which would be the binarized string for each one of the characters, and the corresponding label. Since we ask the users to write a particular letter, we know what that string corresponds to. And then we use this data to actually figure out what these probability distributions are, which would help us define the function f, which then maps from your E to your class, which is basically the classifier itself. Right, so this, that's exactly what this thing here says. So given this training data, we use this data to figure out how this f looks like. And in the OCR example that we saw a couple of slides ago, that essentially would help us kind of figure out what these likelihood probabilities are, and also the prior probabilities often come from your application itself. Okay, this then kind of leads us to the idea of supervised learning. So essentially, supervised learning means that somebody gives examples to the classification system saying, okay, this is how my different classes would look like. And you need to use this information to figure out what are the classes or what are the labels for future data which you haven't seen yet, right? So of course, if you again ask, or if you ask a system to again classify one of the training examples, this is an easy problem. But what is really tricky is that given this examples of, let's say, 100 people writing the letter A, now given a new letter A written by a 101st person, can you figure out what this letter is? And this takes us to the idea of generalizability, which means that how well does our system work for new unseen data. So for all the characters that you have seen already, you need to use that information to build your probability distributions, to learn what the function f is, and then use that information on new data and hopefully come out with a class that actually makes sense there. Right? So this is the general idea of supervised learning, where the models are learned via examples that users give, and the goal often is to come out with that model or that system which would work well for new unseen data. And just a couple of terms that you would come across if you're reading literature from this topic these are the terms classification and regression. So they're quite closely related to each other, with the distinction being that for classification systems, the output is usually a class label. So it's letter A, letter B, letter C, or cats, dogs, or vegetation pixel, no vegetation pixel. So they're often discrete. Whereas for regression, the output is usually a continuous value. So for example, this could be, let's say you have some data points of a car, right? So a car is this big, it's blue, it has, I don't know, this much horsepower. Can I predict the price of this car, right? So when you predict something that's continuous, often the problem is referred to as a regression. And when you predict something that's a particular object, or it's a label, a car, a bus, or a cat, etc., it's often called as classification. Of course, they're much more closely linked in the sense that often you would come across methods where you kind of regress your function f through the training data that you have, and then you can put different thresholds and convert your continuous value into discrete classes. So in this way, the distinction is not that clear, but whenever you come across the term classification, the hint there is that the output is a discrete class, whereas if you come across the term regression, the output is most likely a continuous variable. And in today's lecture, we'll primarily focus on the classification problem. However, the concepts that we will see here are quite general and also essentially work for regression problems as well. Right. Okay, so let's dive a little bit more in to understand what are the various aspects of a classification system through an example. And in this case, the example is the following. So we have certain features of a car. In this case, those features are the engine powers, so and the prices. So the engine powers is in kilowatts, whereas the prices is in in thousands of euros. So for example, one such car is whatever 15,000 euros with 50 kilowatt hour of say engine power, and so on and so forth. So we have these different examples of cars. So in this case, cars are represented by a feature vector E, which constitutes only of two elements, the price as well as the engine power. And we have certain training data, right? So we have this training data which says that if our car costs 15,000 euros and has a power of 50 kilowatts, then it's true. In this case, true is for the fact that it's a family car. So the classification problem that we see in this example is to figure out whether, given this data, so the price as well as the engine power, whether it's a family car or not. This is the classification problem that we're interested in. And like we said, for supervised learning problems or supervised classification problems, we have this training data where for a certain portion of our data we know the label. So we know what is a family car, for example, in this case, and what is not a family car. So for example, this example is a negative one, where if the car costs 7,000 euros and has 80 kilowatt of horsepower, then it's not a family car. And as I mentioned before, the question that the classifier needs to answer is that given this new data point, which is like a car with a feature vector E, which says, okay, this costs 12,000 euros and has 65 kilowatt of engine power, then would this be a family car or not? Right. So this is a classical classification problem like we introduced. And if we actually plot this data, the training data, onto two axes like we show here, on the x-axis we have the price, and on the y-axis we have the engine power. And what you see here are all the training data. So here you see some pluses, which means that those are the examples which are the positive examples, and therefore they are the family cars. Whereas all other data points that you see here, which with the negative sign in between, are the examples of cars which are not family cars. So they are the negative examples, right? And our feature vector consists of these two components, the engine power and the price. And for example, then, yeah, like I said, these are the positive examples, and the other ones are the negative examples. The question that the classifier asks, or if we are to design a classifier, then we need to ask the question, if say a new data point falls in here, would that be a positive example, or would that be, in other words, would that be a family car, or would that not be a family car? And the question is, how can we make this decision? So the whole problem of designing a classification system boils down to this concept. So how can I make a decision for a new feature vector or a new data point that I get, right? So in this example, we'll just show a very simple way of doing this, something that's quite intuitive, and then through that build certain concepts that will help us understand the various terminology that's associated with classification systems, and then go on to actually use them to build different systems, right? So one such classifier, so to say, could be fitting a shape. And to make the example quite simple, we'll fit a box or a rectangle given our data to say if something is a positive example or not. So to say if something is a family car or not, right? So for example, let's consider this gray region here in this rectangle, and we say everything that falls within that gray region is a family car, everything that falls outside is not a family car, right? So this is a reasonable proposition or reasonable hypothesis to actually say, okay, whether something is a family car or not. And of course, one could ask a question, are there other solutions? Of course, there are many other solutions. One is, first of all, the choice of the shape itself is something that is an assumption that we made, right? So nothing stops us from, let's say, putting a circle there or an arbitrary polygon there. But we chose our system or our classifier to be a box or a rectangle, which kind of we say, okay, this is good enough to split my data in a way that I can use it well for new examples, right? But let's say we do assume now that our classifiers are only sets of boxes. Even then, we are then left with the question, okay, which one of the boxes? So it could be any one of these boxes, right? So no matter which box that you choose from the example that is shown here, all of them explain our training data well, in the sense that each of this box has all the positive examples, so all the family cars inside of it, and all the examples outside of it are not family cars. So all the positive examples are inside and all the negative examples are outside. This is a good use of the training data, right? So our boxes, each one of the rectangles, does explain the training data well. Then the question is, okay, which one of these boxes is a good one, right? And let's look at two of these extreme examples, right? So one is the one which kind of sits very tightly around the positive examples, and what is also called as the most specific hypothesis, because it's so close to the positive examples that even if you move slightly outside that box, it would classify it as a negative one. Whereas the other box that we have here, or the other hypothesis that we have here, is what is called as the most general hypothesis, which is kind of sitting on the boundary with all the negative examples. So both are valid hypotheses, and it's up to us to choose which one do we think makes more sense, right? And of course, choosing each one of these boxes would yield different performance, right? So if we choose this outer box, then it means somehow that if, say, something is at the corner at this place where there is a potential ambiguity, whether that is a positive example or a negative example, we might get things wrong. Whereas if we choose this innermost box, we might miss a lot of the positive examples and so on. And of course, and then with this comes, like, there are multiple ways in which you can figure out what is a good box, and this will determine the success of the particular classifier for that application. And some other terminology that we introduce here is called as this version space, where it's the space between your most specific and the most general hypothesis. So there's this whole range of spaces which are valid spaces, and the goal of figuring out what a good classifier is to look in this version space and to choose that particular box which explains or which would give the best performance, particularly for new examples. And this is something that we would see in the next slides to come. And so one specific argument that we could also put in is to choose that box which maximizes the margin. And here the margin is referred to as the distance between, let's say, the closest negative examples and to the, so what we take is the closest negative examples, and we take the outermost positive examples, and we choose that box which is kind of in the exact middle. So in some sense, this is a more robust solution, because if we were to take a box which is, let's say, more closer to the most general box, at the boundary of these boxes, maybe we are making lots of errors for new examples. Whereas if we are too close to the most specific box, we are missing a lot of positive examples. So in some sense, this is one idea amongst many other ideas that one could choose, is to choose that box which kind of maximizes the margin. So you kind of end up in between, such that you explain both the positive and the negative examples as well as you can. And this is one such strategy to use, which often gives quite good results, right? So no matter what box we choose, there will be certain errors that we will make. And this takes us to the next part of this lecture, where we kind of characterize or try to understand what are the different kind of errors that we can make, or that our classification system makes, depending on, for example, in this case, which box that we choose. And so let's continue with this example and get familiar with the terminology that's often used while evaluating a classification system in practice. So again, let's now assume the same example with the family car thing, and this green box that is drawn here is, let's say, this is the correct hypothesis. This is the classifier which is the ground truth classifier, It's something to remember here that in practice, actually we don't have access to this ground truth box. If we would have access to this ground truth box, then that itself would be our classification system and we don't need to worry anymore. But we introduced this ground truth hypothesis here just to understand how good a proposed classification system, a proposed box in this case, is with respect to this ground truth best case box that you can ever have, right? So let's say this is the box that we choose, right? So it's a valid box, for example, because all the positive examples are inside the box, all the negative ones are outside the box, right? However, we see that our proposed classifier is not the same as the ground truth classifier. And this means that we are making certain errors, right? So there are two main kinds of errors that we make when we differ from the ground truth classifier. One is what is called as false positives. This means that we are predicting the negative examples as the positive one. This means that all the cars which would fall in this region here actually are not family cars. So they are negative examples in reality because they're outside the green box in the ground truth classification that we have, but they have been classified as family cars. So these are one kind of errors that we make, what are also called as false positives. Then the other kind of errors that our system, that our proposed classifier here, the proposed box makes, is the ones that are falling in here and in here too. So these are the ones which we which are called as false negatives, which means these are positive examples which we are not able to classify as positive ones. So everything that falls here in reality is actually a family car, but since our box is smaller than the ground truth one, we actually classify it as false negatives. And these are the two main kinds of errors that one makes, especially in a binary classification system. And of course, depending on our application, there are cases in which, for example, it's okay if we have more number of false negatives than false positives, or vice versa. This really depends on our application, and we'd see how this kind of translates into different performance metrics and how that would actually help us choose a particular classification system for our application. So just to go through these terms again. So for example, if a family car is correctly classified as a family car, it's true positive. So this is the best case. And in our picture here, or figure here, so the stuff that's falling in this overlapped region is the true positive. So this is family cars classified as family cars. So this is all good. What is also good is the third thing here, which is non-family car classified as non-family car. So this deals with all the regions outside basically, right? So they're all negative examples, so they're not family cars, and our classifier says that they're not family cars. So these two are the good guys, so to say. We want our classification system to maximize the number of true positives and true negatives, whereas the other two are the mistakes that I mentioned before. So when a family car is wrongly classified as a non-family car, it's a false negative, so you miss those examples. Whereas if a non-family car is classified as a family car, it's a false positive. So it's an error, another kind of error that we make. So of course, this is not just to do with family cars, but these terms are more general, right? So whenever you have positive examples classified as positives, you call them true positives. If you have positive examples classified as negatives, they are false negatives. So you can often think of them as things that you misclassifying, that you missed classifying as the class that you're interested in. True negatives are actually the good ones, where you say, okay, these are not the positive examples, and my classification system actually says that they're not positive examples. And the fourth one being the false positives, where you make a wrong assignment of a negative example as a false positive. And so there are different instances in which, for example, we would like to reduce false positives, or we would like to reduce false negatives, and depending on our application, we would optimize for one or the other. So based on all these possible outcomes, we can actually nicely arrange them into a table as seen here, where on the horizontal we put the actual positive and the negative labels, whereas on the vertical axis you have the classifications or the predictions that you have. So essentially the true positives sit in here, where positive examples in reality are classified as positive examples using our classifier, and similarly on this part of the diagonal where negative examples in reality are classified as negative examples, whereas our mistakes kind of sit on the cross diagonal where negative examples in reality are classified as positive ones, which leads us to the false positive. And actually this also has a special name in the literature which is called as type 1 error. So if you ever come across papers or some other literature where some error is referred to as type 1 error, essentially those are the false positives, whereas the false negatives are also called as the type 2 error, which are essentially positive examples which are classified as negative ones. Right? Actually, there's an equivalent representation to this which is called as a confusion matrix, where instead of saying positive negatives, we argue in terms of class 1 and class 2. Essentially, if 1 is recognized as 1, you put it in here. If 2 is recognized as 2, you put it in here in place of true positives and true negatives. And similarly, the mistakes are on the cross diagonal, where either 1 is recognized as 2 or 2 as 1. So it's kind of an equivalent way to analyze the mistakes or the correct exam or the correct classifications that your classifier is making. So based on these true positives, true negatives, and so on, and also the mistakes that you make in terms of false positives and false negatives, there are actually different rates that are defined. So two important rates here are what are called as the false positive rates and the true positive rates. So as the name kind of suggests, false positive rates are nothing but the false positives divided by the false positives plus the true negatives, which essentially is like what's the probability that a randomly selected example in reality is which is a negative example is classified as a positive one. So this is what false positive rate is, whereas true positive rate is essentially for a randomly selected example which in reality is a positive example is actually determined as a positive example. So these are two kind of important metrics which tell us something about the property or something about the performance of our classification system. And often what happens is that our classification systems have some kind of threshold. So for example, the classifier often can return a probability or a confidence value for a particular outcome. So for example, often say, let's say this is between 0 and 1, and the classifier may be such that it says, okay, with 0.6 probability or 0.6 score, I think that the class is a car or it's not a car, right? However, the threshold that we set for this particular determination that we make is arbitrary, or not arbitrary, but it's something that you can change. So you could set this to, let's say, 0.4, 0.5, 0.6, and so on. And by changing this threshold, the false positives, the true positives, etc., also all change. And this means that the metrics of false positive rate and true positive rates also change. And therefore, when you have to evaluate a classifier at different values of these thresholds, what is actually often more useful is a curve like the one that I show here. So this is a particular curve called as the ROC curve, which stands for receiver operating characteristic. And what you have in the ROC curve on the y-axis is the true positive rate, like we just saw in the previous slide, and on the x-axis is the false positive rate. And the fact that we have a curve is that while we change the threshold, we get different points on this curve. So the red line here actually shows what would happen if you would make a random guess. Given any new sample, you would randomly assign it either as class 1 or class 2. You would actually end up on this particular line. So a classifier, if it's as good as random guess, it's no good, right? So because you're not really using any information from the features to determine what it is. So in principle, we should always want a classifier which is on this side of the red curve. And in the ROC space, is this receiver operating characteristic space, a perfect classifier is that one which would have a true positive rate of 1, which is that all positive examples in reality are actually determined as positive 1, with a false positive rate as 0, which means you don't make any false positives in your determination. So ideally, you want a classifier which is on this left corner here. Right. So just a point to note here often is that this particular kind of analysis is used for data sets where you have kind of balanced number of positive and negative examples. Otherwise, often this could lead to some misleading graphs where, because if you don't have many false negatives in certain applications, this might not be the most meaningful graph for you to evaluate the performance. But in principle, when you have a ROC curve, you change your various thresholds and you choose that threshold, for example, which would give you the leftmost point in this graph to get the best classifier. Ideally, you would want your classifier to be here, but in practice, of course, it's not always possible to have a perfect classification. So you're happy when it's on this left space here. Right. So there are actually two other terms which are also used quite often to evaluate how good a classifier works, and these are the precision and recall. And essentially, precision is also defined as the true positives over true positives plus the false positives, whereas recall, also sometimes called as sensitivity, is basically the true positive rate, like we saw in the previous slide, where it's true positives over true positives plus false negatives. Of course, there are a lot of all the words kind of sound the same, so you need to sit and really pay close attention to this. But yeah, once you have these definitions, these are some terms that would help you allow to determine the quality of a particular classifier, or even help you compare two different classifiers and help choose which one works best for my application. Similar to the ROC curve, we can also make curves with the precision recall values. So you can change your threshold values and you would end up with these curves. So in this case, if you look into papers, you would end up with something like this, where you say, okay, our method, let's say here shown in red, and you compare it with other classifiers, say you have competitor 1 and competitor 2. And in the precision recall curve, it's slightly different from the ROC curve, where you are looking at the right corner. So you want your classifier to sit on this corner here, with of course the precision on the y-axis and the recall on the x-axis. So essentially, if you have a recall of 1 and a precision of 1, which is essentially a perfect classifier, it means that every positive example that's there, you are able to catch it, and precision of 1 means that you don't make any mistakes in the classifications which you make as positive, the examples which you say are positive examples. So if you sit here, it's the best possible scenario, and in general, you want to be as close to the right top as possible. And of course, you would see these kind of plots often drawn when you want to compare multiple classification systems. So same is the case with ROC curve. Also, precision recall is also a similar tool to analyze how good a particular classifier is performing. There are some cases in which it's better to use precision recall curves, and some cases in which it's better to use ROC curves. And in that sense, precision recall curves are often used when your data sets are imbalanced, in the sense that, for example, one of the cases in which it's often used is when you have very few let's say false negatives. And this is one of the reasons why it's important to know which metric to use depending on your training data, if you have a balanced training set or an imbalanced one, right? Okay, so we saw these different kind of plots which help us analyze how a particular classification system works, but it's a lot of data points, and often we want a go-to value to figure out, okay, if I am happy with the classifier, if this gives me the performance that I'm actually looking for. And one such value is what is called as the F1 score, which essentially is nothing but the harmonic mean of the precision recall at a particular threshold value. So of course, in the previous thing we saw, okay, these are all precision recall values, but at different thresholds, right? So at some point you say, okay, I take that threshold which is to the rightmost point, and then, okay, that is my classifier that I'm really interested in. And then for that classifier, you can compute what is called as the F1 score, which kind of combines both the precision and recall values to give you one number in the end. And you can often formulate, okay, I want a classifier which has a F1 score of say 0.8. Right? So F1 scores are such that 1 is the maximum F1 score that you could have, that's the perfect classifier, and 0 is the worst one. And let's say, okay, I'm happy if you give me a classifier which has an F1 score of 0.8. So this is like a one number which gives a score to how good your classifier is, and is something that people often use while choosing classifiers for their applications. Okay, finally, this is kind of one figure where all the terms that I introduced in the previous slides are put together. So it's quite a lot to digest in one slide, but use it as a reference. So whenever you are in doubt, okay, what a particular term means or what different kinds of errors are, it's all in this chart here. So just to look a bit more graphically, the terms that we had seen, for example, the term we had seen of precision, which is essentially true positives divided by true positives plus false positives. This is what precision here is. So this is one of the terms that we had used to analyze, especially in the precision recall curves, whereas recall or sensitivity is something that sits in this column here, where it's nothing but the true positives over true positives plus false negatives. And of course, based on the row or the column you take, there are different metrics. So you have something called as precision. You also have something which is a negative predictive values. Similarly, you have sensitivity and specificity. So if you recall from our ROC curves, we plotted basically between the true positive rate and the false positive rates that we had seen, and therefore kind of all the different metrics that we have seen till now are summarized in this one chart, and is a good place to come back to and use it as a reference. Right. So till now we have kind of seen what are the various terms that are used to characterize the performance of a classifier, the mistakes that they do, the different rates that we defined. And so we kind of have an idea of how to evaluate whether a classifier that I design is good or not. Right. So moving from here, we actually now look at the process of designing a classifier. So what is actually involved in designing a classifier, and we'll look at this in the context of supervised learning. So when we have certain training examples, how does this actually look like? Right. So in the traditional classification pipeline that we have, the first step is what is called as the training step. Essentially what we do in this case is that we collect certain training data. So we go out, we capture certain data. So this could be images from the street, this could be images of the field using cameras, laser scanners, or whatever else that we have. And then the next step is to extract meaningful features from this data, right? Of course, often we can use the raw data itself, but it's more useful sometimes to determine certain features on top of this raw data, which would make it actually easier for classifiers to work well. And so when I say raw data, this could mean like I could take an image which would, let's say, a color image. So you have the R, G, and B values. This itself could be our feature vector. But if you think of it, it's often much more difficult to reason in terms of just RGB values, rather than say if we compute certain features such as boundaries or contours or some other features which capture more meaningful data, which would help discriminate between the different classes that exist. So this is usually the second step. So what are the appropriate features for my application, right? So what makes sense to extract from the raw data that would help me determine whether it's class A or it's class B. Right. Once we have this, then comes the question of actually learning from these features. So when I get a particular feature, so what's the distribution of a class with respect to the features is what you learn, or essentially what we learn is this f function, which is also called as the discriminant function. And you need to learn this using the data that has been collected in the training examples, right? So when we created label training, which meant that we said, okay, this image, for example, has a car, this image has a bus, this is a cat, and so on. So we need to use these labels in order to figure out the distribution of the features or a discriminant function using these label data. And these steps basically form the training step of a classification pipeline. So once we have the training sets, of course, we may have designed a classification system or a classifier which works perfectly for our training data, but it's not very useful if it doesn't work on new data. That's why what is often done is that you test it on different data or new data for which we have the labels, but we haven't used those labels actually in the training process. So it's in a way testing how good our system works for new data that it hasn't seen before. So again, the process goes similar. You get the data, right? You get your raw image, for example, you extract the features, then you determine your classifier based on the F, based on the model that you computed before, right? So based on this step here where we learned the feature distribution, where we came up with a discriminant function, we use that function to actually classify a new data from the test set. And then we evaluate the performance using all the metrics that were just that I have just presented a few minutes back, right? So in the testing data, you have the labels, and then you figure out, okay, this is how good I actually predicted. And then, of course, you make these different metrics, and then you say, okay, does this satisfy my requirement for a particular application? So suppose, let's say, if I wanted an F1 score of 0.8, does my training actually guarantee, or the model that I have learned give me this performance, right? So for example, at some point you realize, okay, I have not actually reached my desired performance. Then you go back to your training state. You either add more training data, so you go out, collect more data, label them, or you design newer features. Let's say, okay, you say, okay, I add this extra feature which I think will really help my determination process or discrimination process. Or you might even change the model that you use to learn from this data, right? So you kind of do this recursively, the training and the testing steps, till you're happy with the performance of your classifier. And once these two steps are done, then basically comes the operation phase, where you basically ship out your classification system, which works on new unseen data, for which of course you usually don't have the labels, right? So this is like the running phase, where you get some input data, you extract the features, and you determine the class labels. And the hope, of course, here is that the labels that you determine is actually true, because these are new data that you have never seen, neither during your training nor during your testing phase, right? And basically this leads us to the idea of what is called as generalization. So a classifier is only really good if it works on new unseen data. If it just works for the examples that we showed, or even just the test data set, it's not very useful, because in practice it needs to work for new data which hasn't been seen before ever, right? And with this comes this term called as generalization, which essentially is given a new set of data which the classifier has not seen before. How well does it work? So what we see here, for example, this kind of matrix here represents the training data. So for example, if you're designing a classifier which determines what are apples, pears, tomatoes, cows, dogs, whatever your application is, and the question is, okay, given a new image of an apple, am I able to say, or is my classifier able to say that it's an apple, right? Of course, there are certain assumptions. Your apple should roughly look like the apples that you have seen in the past. If not, it would be very let's say, unfair to expect that a classifier would work. But of course, it should work for newer images which are at least similar looking to the training set that we have seen. And in general, the best case scenario is that even when you have, let's say, in this case, for example, it's determining cows, you have a cow which kind of looks much different than what you actually trained on, but it still is able to capture those discriminating features from the other classes and is able to give you the prediction that it's a cow. That would be the best case. So the better it generalizes to new examples that it has not seen before, the better is a particular a classification system. Right. So when you talk about generalization, there are a couple of tools which are often, or a couple of terms which are often used in order to understand the properties of this of its generalizability. And one such term is what is called as bias, and the other term which is in there is called as the variance. So essentially, these two terms capture how good is your model in explaining the data that it sees, right? So probably it's easier to explain it with an example. So let's go to the example directly. So for example, your classification system might use a straight line to classify the data. So for example, if we take this example, these red dots that you see in here are the training examples. And let's consider two different models, the one in the green, which is a parabola, and one in the blue, which is a straight line, right? And in this case of our classifier, it's a simple classifier. So for example, the blue line says everything that's on top of the blue line is, let's say, class 1, and everything which is on the bottom of the blue line is class 2. And the same holds for the green line, where everything on the top is class 1 and the ones on the bottom are class 2. So essentially, if you look at this data, it looks like, at least at the first instance, that this blue line is not sufficiently complex to actually explain the data. So the data actually looks like something that's derived from a parabola or something that's more complex than a straight line. And this means that when you use a straight line, you suffer from the fact that there isn't enough model complexity to explain the data, and this means that your model has a large bias. Whereas a parabola is probably the model which best explains the data and therefore has a lower bias. Right? So this is the bias term that sits in there when you often talk about generalizability. But on the other hand, you can also end up choosing a model which is far too complex. So for example, again taking the same example here, now the blue line is, let's say, a polynomial of order 4 or more. And then what this actually does is that it explains your training data very well, but it misses to catch the general trend that's in there. And therefore what we call here is that here the model which is determined by the blue line has a high variance. So essentially, it's too powerful, or it has too many parameters, the complexity is too high to actually determine the trend, rather it fits to the noise in the data. So both are not good. So you don't want large bias, neither do you want large variance. Right? So you want to have a trade-off between how complex a model should be such that it explains the general trend, but it should not have so many parameters that you kind of fit to the noise in the data itself. And we will see that these also lead to terms called as overfitting and underfitting. And this question of a bias variance trade-off is often quite important while choosing what classifier to use for a particular application, given of course a particular kind of training data and the features that you have. And there's a kind of an equation which defines this link quite well, where let's say the error, the mean squared error for a particular prediction depends upon the noise, of course, in the data. This is somehow unavoidable. So because of the training data being basically samples of the true distribution, there is certain unavoidable noise because you just don't observe all the samples that are there. But then there are also errors which are coming from the fact that we make a bad assumption about an incorrect assumption about the model that best fits the data. And then there is the error that comes from the variance terms, where it's the error coming due to the overfitting, or the error that comes from the noise or the variance in the samples themselves. So this is quite an involved topic, and I would encourage you to go to the reference that is given here to understand a bit more about this bias and the variance idea. And like I said, this bias and variance idea is also very closely linked to what is called as underfitting and overfitting. Right? So you might have already guessed, so if our model is too simplistic, it has a high bias, and we are underfitting the data. So this is the case here, where we are using a straight line to fit through our data, which is not a sufficiently complex enough model to actually explain the data we have, whereas overfitting would correspond to this squiggly line in here, where we are actually fitting too much to the noise rather than the general trend of the data itself, right? So we have to take these parameters into account when we design or we propose a new classification system for our application. And there are some rules of thumb which of course help us determine this. So for example, one way to do is kind of start with simple classifiers first. So in the example that I showed, this might be like starting with straight lines, then moving to parabolas, then moving to, let's say, more complex representations, and figuring out which one gives us the best bias variance trade-off. And what always also helps is to actually have good discriminative features. Right? So if our features are already discriminative enough, the classification system or the decisions that have to be made based on those features often become much easier. And therefore, if we're not reaching our desired performance, a hint would be to look at the features. Can we actually come up with better features which would let us reach our desired performance for our classification system? Of course, we must remember that no classifier is inherently better than any other. It's as good as if it works for our application, of course, but also that we need to make certain assumptions that it generalizes to new examples, because the training data is only a subset of what is out there, and therefore we actually never know what our classifier would be tested against. And the goal would be to design something that would be strong enough, or the model would be complex enough to capture the trend, and also be not too complicated in terms of the number of parameters that it fits too much to the noise and so on. Right. So there's another term that you might come across when you look into classification literature, what is also often called as cross-validation. Like I showed you, so usually when we have a classification pipeline, we have a certain amount of data that we go out and collect, and we train our classifier on this data. Then we also have a certain amount of data, often which is taken from the training data and split in a way that it's not actually used for training. And then we evaluate our classifier on that split of the data which hasn't been actually used for training, in order to understand, okay, how well it could work for new examples. But sometimes what happens is that the training data is difficult to acquire, and therefore you only have a limited amount of training data. And in this case, a smarter way of training, so to say, is this cross-validation way of training, where this is one method to do the cross-validation training, or which is also called as multiple fold training. In this case, what I mention here is the 5x-true training, where what we do essentially is we take our data set, the training data set, and then split it into two parts, so 50% each. So if you have 100 examples, we take 50 examples each. Then we use, let's say, the first 50 examples to train our model, and then we use the next 50 examples to actually compute all these metrics that we'd introduced to evaluate the classifier. Then what we do is to actually shuffle our data set again, and then make again a split into two parts, so 50% each, and then do the training and testing again. So essentially we break our original training set into two parts, therefore this cross 2, and then what we do is to repeat this whole process 5 times, and then let's say the performance of our classifier would be defined as, let's say, the average performance on these 5 different swaps, after the 5 different swaps that we have made. So the advantage of this procedure is that we have actually used all the data that sits in there for our training, but also we have tested them on data which has not been used for training, at least in that step. In this way, we are kind of exploiting the small amount of data to train and test together. So when we do this 5 cross 2 cross validation, essentially we end up with 10 classifiers, and we can then choose essentially either the best or the average classifier that comes from this cross validation procedure. Right. With that, I kind of reached towards the end of a general description of how a classification system looks like and what are the steps that are involved in designing a classification system. With that, let's move to our first classification system. It's a fairly simple classification system called as the nearest neighbor classification system, and see how this actually works, and in order to classify a new example as class 1 or class 2 and so on. Right, so the main idea of the nearest neighbor approach is the following. So essentially the model, or this F, is nothing but a subset of our training data set itself. It could be the whole training data set too, or a subset of the data set. And essentially the idea is, given a new feature vector E, we look up in this training data and find that example which is the closest to our current query example, and then assign the same label or the class as that of the training example. So for example, if we take the family car example again, this means that our new feature vector, which would be a combination of the engine power and the price, we would just look up into our training data with our different car examples, find the one which is the closest, so the one which is the closest on, let's say, the power, and also the one which is closest on the price, and then find that example, look out if that's a family car or not. If that's a family car or a positive example, then our new E vector corresponds to a positive class, otherwise it's a negative class. So it's a really simple idea that we have here. So let's see another example coming from the remote sensing application, where in this case we have a multispectral image, so which means that we have RGB intensity values, but with that we also have a near infrared value, which is often quite commonly used in remote sensing applications. And let's say we have in this example 4 different classes: water, land, ground, and other classes. And what happens here is that, let's say for a portion of our image, we label what they are. This could be either a portion of this image or some other image, it doesn't matter. So just for the sake of this example, we would label a portion of the image that we have here. So like I said, we have 4 regions, and we have these examples from those regions which then correspond to the learning step itself. So as soon as we have these 4 clusters, so to say, these are the examples corresponding to, let's say, water, to grass, to sand, or to ground, or whatever classes you have in your application. So this is essentially the training step. Just take your data set. In this case, we take the entire data set as our model. Now, what happens is, now when a new question, a new point comes, so in this case, let's say we want to know what this point is and what this point is, we just put it in our, we just kind of compare it to our samples that we have. And then, for example, in this case, this example is closest to this particular class, which says it's an urban region, whereas this example is the closest to the vegetation. So essentially what we are doing is to look up in a table. So it's basically a lookup table, and then we find that vector which is the closest to our present feature. And of course, it's up to us to determine what is the distance metric. It could be a Euclidean distance, it could be some other kind of distance, but we essentially find the nearest example from our training set and choose the label of that training set as the label for the new queried image. So a really simple idea to figure out what a new what's the class for the new example. Right. Another way to actually see this is the following way. So in the sense that, for example, when we plot this in 2D, we would end up with a diagram like this, where, for example, let's say each of these red dots is actually our, let's say, class examples. So since what we are doing is that for any new query point, let's say the query point falls here, we find the distance to all other examples that we have in our training set, right? And essentially, you could actually do this a priori to any of the data coming in at the query time. And what you would end up with is this kind of regions which are separated, because all the points in this region, the closest example would be this guy here, and all the points in this region, the closest example would be this particular sample here. And therefore, actually we can divide up the space along these different dimensions of E, and then use that to actually figure out what the what the label for the new query data point is. Of course, this also means that there are a couple of problems or problematic cases. For example, even if there's some noise in the data and then one sample kind of skews or falls into the region of a case with many other examples. So maybe it's easier to see here. For example, these are all examples coming from the urban environment, and maybe if just one point in here, let's say here, is a vegetation example, then all the points which are kind of close to that point will now be tagged as, or will now be predicted as, vegetation pixels or vegetation regions. And so this is quite prone to noise in that sense. And therefore, actually, there's a small extension of this approach, what is called as the K nearest neighbor approach, right? So instead of just looking at the nearest example in the training set, or our model in this case, we actually look at K nearest examples. And the idea here is that by choosing a K which is like maybe 3 or 4 or whatever the application kind of supports, we can get a much more robust decision. So we could either say, okay, we look at the 4 nearest examples and then make a majority vote, right? So if I get 3 out of 4 for a particular class, this is the average, or this is the predicted value, or we could make some kind of a weight. So this is some way of introducing some robustness into the system. Of course, so the thing is, of course, then the question comes, okay, now I need to choose K. Before, when we had just the nearest neighbor, you always just looked up to the nearest example, but now we need to choose K. And roughly speaking, so the smaller the K is, the less robust it is to noise, right? So if we take just 2 instead of let's say 5, this means that, okay, we are a little bit more robust to noise, but still, if there are a few noisy points lying in between in the region with other class, then we would still make mistakes. Whereas if we take too far a K, this means that even points which are much farther away might be classified as a different class. So of course we have robustified it, but then we have this extra cost of actually choosing the K well, and often this is a design parameter that one has to play with and kind of use different values of K, for example, and compute the performance metrics that we had introduced before, and figure out, okay, which K kind of works best for my application. Of course, it's one more step, but it does help in general to improve the robustness of our system. So this is one really simple approach where the subset of the training data itself is the distribution, or is the model that we use to determine the class or the prediction for a new data set. The next the second approach that we would see today is the one of decision trees. Essentially here the idea is of asking a series of questions, and the answers to this question would lead us to assigning a particular class for the new example that we have. So this would end up having in a tree of questions, and then by reaching to the leaf nodes, we would have the prediction for that particular example. And we'll actually go into the details and see how this works, right? So like I said, so essentially decision tree, what it does is it breaks up your input space into different splits or into different regions, and each of those regions actually corresponds to a particular class. So if you again go back to the example of the family car that I showed at the beginning, where we had chosen these splits in terms of rectangles, right? So we took a box and we said that everything that's in the box is the positive class and everything that's outside the box is a negative class. In some sense, that is also a decision tree where, let's say, we said, okay, if the car is between or it's greater than this many euros and less than this many euros, and the power is greater than this many kilowatt hours and less than this many kilowatt hours, this is in a way a decision tree, right? So you're asking these different questions, and this splits our input region into a particular, in this case, a box, which tells us whether a new example, if it falls in that box, is a positive one, otherwise a negative one. Of course, the decision tree is a more general principle where splits need not only be rectangular boxes, but they could be any shapes, since you can ask a series of questions that kind of carve out different regions in the space that are much more complex than just a square that we have. Right. So let's see again an example here how decision trees work and what are the different steps in using a decision tree for the classification problem. So let's say we have two classes, the squares and the circles, and our goal is to come up with a decision tree, the classification system in general, which distinguishes between the square points and the circle points, right? And as you see here, we basically have two properties, x1 and x2. So these are basically the elements of a feature vector E. And then what we want to come out with is basically this kind of tree here, which would let us figure out whether a new example would actually be a square or a circle. And this is essentially the training part of this step, where the examples here correspond to some training set, where if we say that, okay, all the squares are those points which lie to the right of W10, which is some kind of a threshold on my x1 parameter, and up or above the W20 threshold on the x2 dimension. So this is equivalent to actually breaking up or splitting my space into kind of this region down here and this right corner region up here into the region for, let's say, the circles and the squares respectively. So anything now that falls in here should correspond to the class omega 2, whereas anything that falls in here would now correspond to the class omega 1. And an equivalent way to look at it is in terms of this tree, and essentially this is what the training process is supposed to do. So given this data, I need to figure out this tree so that I can actually do the classification for new examples as they come, right? So let's see how this tree looks like, right? So for a new example, for an example where let's say this particular tree is built such that it explains this training data correctly. So it says, okay, for any example, let's say if we take this example down here, it is on x1 axis greater than the threshold W10. But let's actually go through the tree and see how this works. So if the question is x1 greater than W10? So if we take this data point here, yes, it's greater than W10, then we end up down on this kind of the branch here. Then it says, okay, check if x2 is greater than W20, and x2 is actually less than W20, and therefore the answer to this question is no, and therefore this corresponds to a circle example. And that makes sense because we actually checked this for an example which was a circle example. And in this way, this tree or this set of series of questions represents the split in the input space, which would help us or which would be actually used for classifying in the next steps. So if you look at these decision trees, it has specific elements. So we start at something that's called as the root node, which asks the first question about, let's say, some dimension of your input space. Then you have something that are also the decision nodes. Of course, the root node is also a decision node, but in general, a decision node is one where you make a test, you ask a question, is something greater than or less than or something. Of course, this is one kind of questions. Your questions could be equality questions, it could be much more complex operations, but in general, it's a question which tests a certain properties, let's say, on your E vector and makes a particular decision. And then what is sitting inside is called as the test function. So this is the logic that you actually use to determine from your feature space where or how to actually split your input space so that it helps you determine the class. And when you reach one of these end nodes, what are called as the leaf nodes, you have your decision. So if you end up in this node of the tree, you know that that example corresponds to a circle one, whereas if you end up here, that example corresponds to a square one. Right, like I said, so the kind of the logic part of the decision tree is this test function. So it's important to design this test function in a way that actually helps further the classification decision. So let's say if your E vector is a long vector, so you need to ask certain questions on this E vector or make certain tests on this E vector, which would actually help you discriminate between different classes that you have in there. So also sometimes these nodes which make the decisions are also called as split nodes, because at this point you would either have a yes answer or a no answer, and you would go into different directions on the tree depending on the answer that you have. And finally, the leaf node is actually the node which will tell you, okay, whether this is class 1 or class 2, and in principle other classes if you have it in your system. And so if I just kind of summarize the classification system as an algorithm here, essentially you start at the root node. So you ask your first question, then you check the answer to this question. Do you end up in a leaf node? This means that, do you know, okay, after this test, does it fall into a node which says it's class 1 or class 2? If yes, then you're done. So for this new vector that you have, the new query point that you have, you know what is the predicted class. But if not, then you need to perform the next test on the branch that you reach to, on the node that you reach through the yes branch, for example. And then you then go back to question 2. You always ask, am I now in a position where I can make a determination or not? And you kind of do this recursively until you reach a leaf node. And this is how for every new example, you can actually determine a predicted class for that query point. Right. So this was how actually the process of determining what is the prediction for a new data point. But actually we skipped over some of the details as to how do we actually learn a decision tree, how do we come up with these questions that we had, or what is the arrangement of these questions that would lead us efficiently towards a prediction for the new data point. And it so happens that the order of the questions that you ask is actually not that easy to determine which is the order. So it's actually an NP-hard problem, which essentially means that it's computationally very complex to or very tough to actually find out what is the optimal order, for example, which would give me the prediction for my data point in, let's say, the fewest number of questions, or the one that's more accurate, and so on. So of course, for the example that we showed there, where you just had 2 axes, this is fairly simple. You can write down all the combinations and then choose the best one based on the metrics that you choose as the performance indicator for your classifier. But in principle, if you have a large dimension vector, like 1,000 dimension or even a 1,000,000 dimension vector, then the order in which you have the question becomes really important. And the question then becomes is, what is a good strategy to actually determine these splits, or what's a good order of questions that would actually make these splits effective. And there's actually an idea or a heuristic that people use when designing these decision trees, and which essentially it boils down to the following idea, that the question that you should ask is such a question which would make a split that it separates out examples from your class 1 to class 2 as well as possible. So another way to look at this is that when you ask a question at, say, level L, then at level L plus 1, which are also referred to as children, the sets that are formed at level L plus 1 should be as pure as possible. And when I say pure here, what is meant is that, let's say, the yes corresponds to a lot of sample points of class 1 and very few of class 2, and vice versa for the no. So essentially we should ask that question which separates out a major chunk of your training data into one set and another smaller part of the training set into the other one. So we always want to ask those questions which makes these kind of rather effective splits. And a way which is a metric that is actually used to measure this purity or conversely impurity is through what is called as entropy and a similar other index called as Gini index. So basically, given these indices at each step, you compute this index, and this gives you an idea of how good the splits are or how pure these splits are. And let's look at actually how these measures are defined. So we'll look at mainly the entropy as an impurity measure. So this entropy is something you would be familiar from information theory. Essentially, the entropy here, capital H, is defined over the different classes omega i's as the probability of that example being omega I. So P of omega I times log of P of omega I, and then you sum it up over all your examples. So in a binary case, it's class 1 or class 2 basically, and then you have a negative in front of it there. So what happens in this, so what this kind of gives you is a measure of how pure or what's the constituency of a particular region in your input space. So for example, here we plot it for a binary case where omega is either class 1 or class 2, right? And therefore the entropy boils down to this formula here on the vertical axis, which is nothing but P times log of P, plus it becomes 1 minus P, because since there are only two classes, the probability of the other class is nothing but 1 minus the probability of the first class, and you end up with the curve that you see here. And the way to understand this curve is the following way. So on the y-axis is the entropy, and on the x-axis is the probability of a particular sample belonging to class 1 or class 2. So let's say we are analyzing the probability of a sample belonging to class 1. So this means that if the probability of element belonging to class 1 is 0.1, this somehow corresponds to an entropy which is quite low, in this case of 0.3 or so. So we would want those splits which would result in smaller entropies. So right, so we would want almost all the elements to either belong to one or the other group, right? So a similar thing happens on the other end. So if the probability of an element belonging to the first class is 0.9, again the entropy is something small, right? So essentially the worst case in this scenario would be what happens at the center. If the probability of an element belonging to class 1 is 0.5, this leads to the highest entropy, which essentially means that you have a split where there are as many elements coming from class 2 as there are from class 1. So in terms of purity, this is the worst case scenario. So essentially we want to be towards one of the ends, which would ensure that the splits that we make are those which are consisting entirely or almost entirely of one of the two classes. So with this, using this entropy as an impurity or a purity measure, the idea is quite straightforward. So we select that split, right? So we ask that question which reduces the entropy the most. So right, so if we have an entropy before the split made is h of omega here, and this is the entropy that is made after the split. So we should make that split that reduces the entropy the most. So this means that we want the change in entropy to be quite high. So in the end, we would like the splits to almost entirely consist of elements from one set or the other. So by following this kind of heuristic at each step of the decision tree, so this happens during the training step. So as we go down the levels, we ask this question continuously. Does asking this question make my splits such that I have a lot of examples of class 1, for example, in one side of the tree and only very few on the other side of the tree. So this is how this heuristic is used during the training process. And just like entropy, there's an alternative index called as the Gini's index, which ends up being very similar to the entropy measure. So here you see in the blue is the Gini index, whereas in red is the entropy value. So it's roughly the same for practical purposes in terms of its effect on splitting, but there are these two different options which you can actually use to do the splits, right? Of course, this helped us. So using this purity or the impurity measure essentially helped us determine the question which would split the region into split the input space, so to say, into different regions. But we still need to decide when to actually stop this splitting. Of course, like we saw in the example that I showed before, you can split when every single element has been properly categorized or has only one class, right? So we need to ask questions till you end up with only one class in your leaf nodes. However, there is a small problem with this. So often, because the training data has certain noise in it, or there may be certain errors in the training data, this means that if we really go till the end part where all the splits are completely pure, which means that they only have elements from one class, we might be actually overfitting. So this again relates to the idea of bias and variance that we had seen in the beginning of in the mid of this lecture, where by going completely till the bottom of the tree where we have splits which consists of entirely one class, we actually might be overfitting due to the noise in the training process. So often in practice, what is done is that you have a threshold. You say, okay, if let's say 90% of the elements in one of the split belongs to, let's say, omega 1, so class 1, then I stop my my splitting there. So that would be one of the leaf nodes. So this way we can kind of take care of the noise that's inherent to the process of the training step, right? Yeah. So just as a final slide on the decision trees. So the thing is that in the end, decision trees give an easy way to build a classification system which are based on simple yes or no questions, and quite often these work really well on high dimensional data, which makes a split into split in the input regions very efficiently in very few steps. And another nice property of using decision trees is that since the test function is left up to us, we can kind of make checks which are of different kinds. So we can make equality checks, we can make checks whether they belong to a certain category and so on, which gives us quite a little bit of leeway or space to design a classification system that takes care of or that intrinsically allows for mixed kind of features, mixed data features to be used for classification purposes. And often certain heuristics such as the entropy of the splits are used while training to make the training process efficient. So with that, I reach towards the end of today's lecture, where basically I gave you an introduction to what classification systems are like, how to actually build a simple classifier, what are the different stages of a classification system, and in particular we focused on the supervised learning paradigm, where we have certain examples which are used in order to train the model which is used in the classification system. And then at the end we also saw two different classifiers in terms of the nearest neighbor classifier and the decision trees, which are basically quite simple classifiers but lead to really effective systems for classifying data of different coming from different sources. And also, not to forget, we also introduced quite a few metrics to actually evaluate, once you design a classifier, actually how good that is. And this is also kind of critical in figuring out which classification system should I actually use for my application. So with that, I would also like to point you to some literature if you're interested in learning more or going into depth. This is a book where you should definitely look, and these are some of the chapters that you might want to read up. So with that, I come to the end of this lecture, and I thank you for your attention.